Remember that ionization energy is the amount of energy needed to remove a valence electron from a neutral atom. So we can measure ionization energy in what is known as kilojoules per mole or in electron volts. So here's an example. Lithium, which is neutral, we would have to apply a certain amount of energy in order to remove an electron from lithium. And in doing so, lithium becomes a positive cation with a charge of +1. And there is that electron that we removed. This value here off to the side, 572.3, is the amount of energy needed in order to remove that valence electron. So here, just showing if I want to remove this valence electron, there's a certain amount of input of energy that's needed in order to do that, and we call that ionization energy. Here would be what the graph would look like that we did in class. When you label all of the peaks, we notice that we have the noble gases at the peaks, and at the valleys, we have the alkali metals. Notice that this is the opposite trend that we saw with the atomic radius and atomic number, where the alkali metals were at the peaks and the noble gases were in the valleys. So what does this tell us? This tells us the first ionization energy. So how much energy is needed to remove the first electron from these atoms? And we notice that it takes a lot of energy to remove a valence electron from the noble gases compared to the alkali metals, which don't require as much energy, and hence why they are in the valleys. And we notice the corresponding energy value much lower for lithium compared to helium or compared to neon. Now, notice with this graph, we can still state some trends. We have an overall upward positive trend happening going from lithium to neon, so that's considered to be a period. Same from sodium to argon. Now we notice that we have some little blips here, and some of these little blips occur with some of our transition metals, and that gets a little bit more tricky when we get into quantum chemistry and different orbitals and so forth. But all you need to know is that the trend is moving upward as we move from one left of the period to the right of a period. Okay, so as we go from from potassium to krypton, that is one period. Now, when we look at down a family, I would have to look at a family specifically. So let's say we were looking at the noble gas family. As we go from helium to neon to argon, we're moving down, and we notice that the ionization energy is also getting less. And the same thing as we go from lithium to sodium to potassium, whatever family we're in, if we're looking at the alkaline earth metals, beryllium, magnesium, as we're moving down the family, it would appear as if the ionization energy is also dropping. So it decreases as we move down a family of elements. Notice that I just do capital I dot, capital E dot for ionization energy. Now, why is that? A couple of different reasons. So here we have potassium over on the right and sodium on the left here. So potassium is the bigger atom. And so it has more shells and therefore a weaker nuclear attraction because those valence electrons are farther away. And so these inner electrons actually shield the valence electron from that nuclear attraction. So it's much easier to remove an electron from an atom that has a valence shell that is farther from the nucleus. Okay, so size comes into play, but also something called shielding effect. So the atom gets larger as we go down a column or family. Therefore, the valence electron is further away. There's less nuclear attraction, and it's easier to remove that valence electron. So here is just a little picture to sort of illustrate and explain why. Trends across a period. Well, we just talked about as we move from left to right, it would appear as if we have an upward trend happening, even though we've got some little anomalies there. it tends to increase as we go left to right. Now let's take a look at why. We already established with atomic radius, as we go left to right, we know that the atom is getting smaller, even though they have the same number of shells. And this is due to the fact that you have an increase in protons. If you have an increase in protons, you have an increase in nuclear attraction. If that happens, then it's much harder to remove an electron, and that requires more energy. So, if you've got increase in nuclear attraction due to the increase in protons, it's going to require more energy to remove a valence electron. Metals on the left tend to have low ionization energies and form cations, and they tend to give up their electrons more easily. So there's our general trend as we move left to right and as we move top to bottom or bottom to top. Ionization energy really does help to explain the reactivity of metals. So what you need to know is the lower the ionization for any given metal, the easier it is to remove a valence electron, the more reactive it will be. We can try some of these. So when you take a look at between sodium and magnesium, which would have the larger first ionization energy, let's take a look at your periodic table and let's see how you would do. So between sodium and magnesium, let's take a look at where are they located on the periodic table. Sodium is an alkaline metal. Magnesium is an alkaline earth metal. The larger first ionization energy means it takes more energy to remove an electron. So in this case, that would be magnesium. When we compare magnesium and aluminum, aluminum would take more energy to remove a valence electron. Therefore, it has a higher first ionization energy. When we look at calcium and beryllium, they are within the same family or column. And we notice that calcium is farther down. So it is going to have electrons that are farther away from the pull of that nucleus. And so it will be quite easy to remove its electrons. So in this case, beryllium would have the higher first ionization energy. And then let's take a look at fluorine and chlorine. And we see that fluorine is higher up compared to chlorine. It's smaller, tighter hold on those valence electrons, much harder to remove, greater first ionization energy. There's something called the second, third, and fourth ionization energies, and that just indicates how much energy is needed to remove the second electron, the third electron, or the fourth electron. When we are looking at the ionization energies for sodium, here's the amount to remove the first one, here's the amount to remove the second one, and so forth. You're going to notice that there's a huge jump to remove the second electron from sodium, and that's because now you are trying to remove a second electron from a full outer shell. Remember that sodium is an alkali metal and it only has one valence electron. So when you remove that, you're down to an inner shell, and whoa, if you're trying to remove an electron from a full octet, it's going to require a lot of energy. And so that's why you see such a big jump going from the first to the second ionization energy for sodium. And the same thing happens for magnesium. A big jump occurs when you try and remove the third electron compared to the first and the second. Magnesium has two valence electrons, takes this much energy to remove the first, takes this much energy to remove the second, but now once you've removed that second electron, you're down to a full octet, a full shell. And that's why we see such a big jump in order to remove the third electron.